So thank you very much, first of all, to Miguel, Irene, and Kumrun for inviting me to give this seminar. It's a pleasure to be here. So today I will talk about work that I did throughout the last year or so with different people that you see here on this slide. And even though now I'm at LMU, I just arrived here in January, and most of the work was done actually at Penn. So that's why I also included Penn on the list here. And I was funded by DFG actually. So before I go to the outline of my talk, let me start with a motivational slide that might be maybe surprising to some of you, namely the gauge group of the standard model. So if I ask you, what is the gauge group of the standard model? The actual answer to the question is actually, I don't know, and nobody does. What we do know is the gauge algebra of the standard model. There we have the SU3, the SU2, and the U1. So strong, weak, and hypercharge, as you know it from your QFT courses. However, there might be different global realization. And throughout that talk, if I say global, I don't mean anything to do with global symmetries, but I mean the global realization of the gauge group, which is gauge group versus the gauge algebra. And in fact, for the standard model, we could map it, we could divide by a discrete factor, and this discrete factor could be trivial, could be Z2, Z3, or Z6, and we actually don't know. And the difference for that would be the different spectrum of line operators in these theories. And well, one of my motivational slide here is, wouldn't it be great if the Swampland program could tell us what the actual gauge group of the standard model is, not only the gauge algebra. Spoiler, I will not be able to tell you the gauge group of the standard model in this talk, but maybe I give you some hints where to search for hints of how we can constrain it further and further, and maybe at some point we can actually nail it down to some of these realizations. Okay, so with that, the outline of my talk, first I will tell you what is the difference between the gauge group and the gauge algebra in gauge theories in general, and what it has to do with these center one form symmetries. Then I will come to one of the most important points for us, which is the mixed anomalies that are actually affected by these center one form symmetries. And from that, I can relate to constraints for 8D supergravity theories. And in fact, these are so strong that we can approach string universality quite a bit in the comparison with F theory on K3 manifolds, for example. Then I will actually focus more on the geometric side of the string constructions, which is the F theory side and Mordell-Weil torsion, and how these different global realizations of gauge groups are realized there. And I will come to the point how that is all related with modular curves and the spectrum of branes in my theory. And finally, I will come to a point where these branes are also constrained by something known as the cobordism conjecture. And this will be the end of the talk. Okay, first of all, let me describe something probably very simple to you, which is U1 abelian gauge theories and the charge quantization, the magnetic flux quantization in there. So the usual story is you have a U1 gauge theory, you have dynamical charged particles, and by something like Dirac quantization, you will know that your magnetic fluxes are quantized. Your magnetic charges essentially are quantized. And this can be done, as I said, by Dirac quantization. So you can calculate something like the angular momentum of the field content, and you constrain that to be a multiple of h bar over 2. Or you can do it in terms of the wave function and demand that the wave function is actually single valued. And this also will tell you that, in fact, depending on the charges of your dynamical particles, the flux integral has to be quantized. However, the dynamical particles are not needed for that, because I can write down an operator, which is given by this Wilson line here, which is a line operator, that has no mention of this dynamical charged fields whatsoever. And now you can consider, for example, a sphere with a U1 gauge theory on it. And then you can just say, okay, I define this line operator to be here and I want to evaluate it. And then I have two choices by Stokes, right? So I can complete this line in the interior, or I can complete the line in the exterior. And of course, the physics should not depend on what choice I do. And from that, I will find exactly the same charge quantization without having anything to do with the single valuedness of charge field wave functions or the presence of dynamical particles. So in a sense, what the take-home message from this slide is the more charges you have in your line operator spectrum, the less fluxes are allowed, right? So the more charges, meaning that the smaller values Q you allow here or here, the larger the fluxes will be. Now, if we go to a non-abelian gauge theory, the story changes a little bit because, for example, trace F vanishes now identically, but still you can define line operators, electric line operators. Now, these are not labeled by the charge Q, but they're rather labeled by the representation R. And additionally, before we had abelian gauge theory, so the gauge boson was uncharged. Now we're in non-abelian theory, meaning that we always have the dynamical gauge particle defined by the gauge boson itself, which transforms in the adjoint representation. So the really meaningful part of these line operators is contained in like the representation labeled modulo the adjoint representation. And as before, we can demand the absence of representation, and this will modify the gauge group accordingly because we will have more fluxes allowed. So for example, you can take a simply connected gauge group, for example, something like SUN, and then you can demand the absence of all the representation that transform under the center in this line operator spectrum. And this will turn this gauge group SUN into SUN mod ZN. And in turn, because you do that, you get these additional fluxes. And these come in this guise of generalized Stiefel-Whitney classes, which basically tells you that you cannot lift all the SUN mod ZN bundles to SUN bundles. Sometimes they're also called Toft fluxes because actually he was the first one to write them down even already in the late 70s. And they were also used, for example, in a paper by Witten to calculate the different supersymmetric indices in these different theories, and they will have an effect on that. Right? And these Stiefel-Whitney classes will be specified by these cohomology classes, where X is our space-time, and Z is given by the discrete factor, which is a subgroup of the center that I mod out. Okay, so I told you that somehow for the definition of the global realization of the gauge group, these line operators are important. And in fact, it was shown by a couple of beautiful papers that this line operator spectrum is exactly what you need to define the global gauge group. And these play an important role. Now, however, you have these extended one-dimensional operators, these Wilson lines, if you wish. And just like the usual point-like operators in your field theory, they're charged under symmetry. However, now it's not the charged things are not point-like, but extended. And correspondingly, the symmetry operators will have a different dimensionality. So usually what you do is you have a point-like operator, you're surrounded by something, you act with a symmetry transformation, and you get the symmetry transform theories. Now, in order to link the operator, however, if it's one-dimensional, I don't have to do it with a sphere in 3 dimensions, for example, but I have to link it with a different dimensionality operator as pictured by this here. And this will be the main theme of this talk here. So we will concentrate on the center one-form symmetries, the electric center one-form symmetries in non-abelian gauge theories in various dimensions that then specifies the global realization of this group. So now that I have this higher form, this discrete one-form center symmetries, these can be, as usual symmetries, broken or gauged. So what does it mean to break these higher form symmetries? Well, this is actually done explicitly by the presence of charged particles. Because then if I have these charged particles in my theory, then I can let this Wilson line end on it. And if I go back to this slide here, so if I can actually break this Wilson line, because now these can end on the charged operators, this will not implement the symmetry transformation anymore because I can unwind sort of. So this is why the presence of charged fields actually corresponds to explicit breaking of the center one-form symmetries. in the same way, I can gauge the center one form symmetries. And I do that as usual by coupling it to a background field, which in this form, now we're in one form symmetries. So also the background field has to have one more dimensionality. So actually here it's a two form. And then I sum over all allowed configurations. And in fact, these configurations are identified with the Stiefel-Whitney classes before, and now you can already see what physically happens. So in summing over all these Stiefel-Whitney classes, I secretly sum not only over, let's say, SUN bundles, but I sum over all SUN mod ZN bundles. And this is exactly how my modification of the theory works, right? And how the gauge group is defined in terms of this gauging process. Okay, but whenever I want to gauge a symmetry, I have to be careful that it is actually a symmetry, right? So if I want to discuss a model that has a G over Z, where Z is the subgroup of the center, I have to make sure that it's not broken explicitly. So the dynamical particles or the dynamical operators have to be absent. And on the other hand, it cannot be broken by quantum corrections. So there should not be any anomalies of any type. So pure anomalies in the theory or mixed anomalies, as we will discuss in this paper, in order to gauge it and in order to then obtain this modification of the global realization. And this will be one of the big players in this talk, is the mixed anomalies that involve the center one form symmetries. And similar discussions have appeared in various dimensions. We'll focus on a short aside on the 60 part and then mainly on the 80 part of supergravity of these theories. Before I do that, let me generalize the discussion of these discrete fluxes. In fact, what you can do is you can take two of these discrete fluxes and pair it into something that is a four form. So this is the rigorous thing to do. This is the so-called Pontryagin square, where I take two elements of this discrete cohomology and it pairs into a discrete cohomology of rank 4 with possibly a different coefficient group, which is specified by some subtle issues. I'm a little bit lying already when I say that this is the cup product of this discrete two forms I defined before. And I'm lying a bit more when I do this wedge product of the theory. However, as a physicist, this is essentially how we can understand it, because it's something discrete inside the instanton density of your non-abelian gauge theory. And you can actually see that because in theories with SUN mod ZN, for instance, you have fractional instantons as measured in terms of in units of the instantons of the SUN theory, right? And this is given, this fractional instanton number is specified by this Pontryagin square, which is an integer number times a fractional prefactor. And this fractional prefactor depends on your gauge algebra that you take.
Markus, can I ask a quick question?
Sure.
Is there any circumstance in which these subtleties that you just glossed over matter? Like, can you get any extra mileage by in any? I understand this is not what you're doing today, right? But is there any circumstance in which this is, you can get something?
Yes, I think there are. So one example that I have in mind is if you think about axion inflation. So if the inflaton is actually an axion, right, then sometimes you want to stretch your inflaton potential. Now the period of your axion is determined by the instanton number, essentially, right? The periodicity is given in terms of the smallest instanton. So there was actually a paper by Yonikura, I don't remember the probably 2017 or even earlier, where he uses that in SUN mod ZN, so where you have this modified version that you can actually enlarge the periodicity of the axion. So that would be one application of where these things matter. And I'm sure there are others if you think more harder about it. Right, so these are the fractional instantons in my theory. Now, why do these matter for us today? Well, because a lot of actions have a coupling to other fields of the instanton density. So here we have the guy that I just talked about. This is just in 4 dimension. It would be the coupling of an axion to this instanton density. In 6 dimensions, this is just a version of the generalized Green-Schwarz mechanism that is actually used for the standard anomaly cancellation. And in 8 dimensions, there would be a coupling of, for instance, of a 4-form field to the instanton density. And this coupling does indeed arise in n=1 supergravity in 8 dimensions. And it arises in a universal way, which we'll discuss later on. Now, what is important here is that these dynamical fields now that this instanton density couples to come with their own sort of gauge dynamics, right? So these are form fields except the axion. So they come with their own gauge dynamics. So what you can do is you can do these small gauge transformations, which would be shifting this form by an exact form, or you can do a large gauge transformation, which would be by shifting by this class in HD of integer cohomology, sorry, essentially, right? But now keep in mind, we have the instanton density here that is usually integer. And now we did a modification which allows this to have fractional values. So what is important here to remember is that anomalies are given by, I take a theory, I do a gauge transformation, and my partition function develops a phase, right? And this phase is indeed produced here in case I have this non-trivial background for C2 with a fractional coefficients in connection with this large gauge transformation for the form field it couples to, which has different dimensionality depending on the space-time dimension that you're interested in. So this is really a shift of the partition function by a phase once you do this large gauge transformation in these dynamical fields. So one way to phrase it is there is a mixed anomaly between the center one form symmetries, which is specified by this guy here, and the large gauge transformation for my dynamical higher form fields. Or you can also apply something like a tadpole argument, where you say your theory in principle wants you to cancel this guy by adding a physical object, but your theory does not contain this physical object that does the job. So that is another way to phrase it. And I know that I think Miguel is more in favor of this second argument of a tadpole-like cancellation. So sorry.
Can
now
I ask,
yes, sure.
The normalization you're using here, is the normalization appropriate for G before you quotientify the center symmetry?
Sorry, so I'm very cavalier about, you know, these cup products and prefactors and so on and so forth. So my conventions are that this all is integer, and the only fractional thing enters through this alpha here, right? And,
okay.
and in principle, there would be a 2 pi here, but I forget about it because, sure. You know, so the only fractional Vorisum part is contained in these alpha factors. Yes, thank you. So now I have this, in principle, this mixed anomaly. And I told you before, if I want to modify my global gauge group, I have to gauge the center one form symmetries, but now there is a potential obstruction to it, right? So if I cannot gauge it, I cannot consistently get this modification of the gauge group, and I will have a restriction, right? And this is something that we want to explore in the following. And maybe this is a good place to pause if there are any further questions, because now we come really to the applications of this. Okay, then I continue. So before we go to Swampland and supergravity constraints, let me just give one slide, because I think this application is very interesting on its own right, on 60 SCFTs. And we know in these 60 SCFTs on the tensor branch, which have a beautiful realization in terms of geometry of F-theory compactifications, we know that these couplings that I described before arise everywhere, because I have a bunch of tensor fields that couple to the instanton densities of 60 gauge theories in the following form. And even more, these prefactors are now specified by the intersection numbers of my F-theory compactification space, right? So this is non-compact spaces, but with compact divisors, and these compact divisors and how they intersect will fully determine these prefactors here. And again, now I do my variation in a non-trivial background of my center one form connection, and I will find that these are potentially fractional. So what this means is that there might be an anomaly, a mixed anomaly in the Higgs, in the tensor branch of these 60 SCFTs that obstructs the gauging. So let's do two simple examples. Let's consider the non-Higgsable cluster on a -3 curve. So this means that there is one tensor multiplet coupled to a SU3 gauge connection in the following form. And actually this prefactor here is given by -3. Now this alpha for SU3, if you look it up, it's 1/3. So what you get is you get -3 times 1/3 is equal to -1. So there is no fractional here and no fractional value in this gauge variation here, and there is no problem in gauging it. And indeed, you can find an explicit F-theory construction for 60 SCFTs that have this center one form symmetry gauged, and on the tensor branch you will find a gauge theory that is given by SU3 mod Z3. Now a different example is here in terms of these E6 superconformal matter. Again, you have the same guy in the middle. It's the -3 curve with a SU3 algebra on top, and you would encounter the same term here, but there are more tensor fields coming from these compact curves of self-intersection -1. And since they have intersection 1 with this middle curve here, actually now I get a prefactor 1 times 1/3. So what you will find is that you cannot simply gauge this center one form symmetry in the interior without doing anything else. So in this situation, you will find a mixed anomaly. However, what you can find is that there is an anomaly-free combination involving also the center symmetries of these E6 flavor factors on the outer ends. And there's again explicit F-theory constructions of these models where we gauge part at least of this center one form symmetries on the tensor branch of the 60 SCFTs. A small curiosity is whenever there is an anomaly, there is also charged massive string excitations in these theories here that are charged under the center one form symmetries. So sort of this anomaly which is a pure EFT, very low energy constraints, seems to know that there are some heavy particle states that are actually explicitly breaking it. And yes, Miguel.
Can I ask quickly? So you say if there's an anomaly, there's charged massive states, but this is not a two-way street, right? So you could have, like, you could also have like a situation where you have a gauge group with a center one form symmetry, which is not anomalous and it's still broken. Does that actually happen in F theory?
So in these surveys,
like if you have a simply connected group and
right.
there's no anomaly and in the center one form symmetry, but still the global form is, let's say,
it doesn't seem to happen. It doesn't seem to happen. It doesn't seem to happen. Yes.
So you're saying this is a two-way street. Okay.
It seems that way, at least in the 60 F-theory compactifications. And if you have been to some of the recent talks of Woody Taylor, for instance, he also announced this sufficient massless charge sufficiency condition, which would be one aspect of this guy. And it's even on the massless spectrum. This is not even massive, this massless spectrum.
I'm getting a little bit ahead, I think, of what you're going to be talking about, but this is not the case in 8 dimensions, right? In 8 dimensions, we can have both sometimes.
In 8 dimensions,
I thought maybe I'm wrong. Okay, well,
yeah, let's maybe come back to the question later. Yeah.
And, sorry, Markus, before,
yes.
Sorry, yeah, just to make sure I understand. So what doesn't happen? So you're saying that doesn't happen, that it's that is not an anomalous, so you can just break it, or?
No, I think, okay, sorry. Yeah, I have to be careful here. So I think in the realization that we constructed, whenever it was anomaly free, we could also gauge it. That doesn't mean that you have to gauge it. I think that is what Miguel was what Miguel was referring to. However, we haven't checked the massive string spectra in these circumstances. So I'm not entirely sure. So this is done by some complex structure deformation that I will come back later to what they are in the K3 at least, but the same thing exists here. We just didn't investigate if what the massless string spectrum gives us in 6 dimensions because we focused on the SCFT side. But there it was like, if there is an anomaly, we could always find these charged massive strings. Okay. With that, let's come to one of the most important results, I would say, today, which is the constraint on 8D supergravity theories. So again, we find this topological coupling now of this 4 form to the instanton density. We again find the possible mixed anomaly with the large gauge transformations related to these fractional coefficients here. There's also like this Ki squared, which depends on how I want to embed these things. But what we gain compared to the 6-dimensional framework is that now there's only a single 4-form field and it couples to all the field strength, right? So now I don't have a lot of different tensor fields that couple in a different way. It's one 4-form field that couples to all of them. And I get this constraint that if I want to gauge the 1-form center symmetry, so if I want to modify the gauge group accordingly, this guy has to be an integer. So let's take all of the gauge algebras that appear to be SUN. Then the constraints reads like this, and you see that it's actually non-trivial, right? So there are restrictions on the global form of the gauge group realized in 8D supergravity. Well, now you could say, well, it's non-trivial, but you haven't told me anything about these prefactors mi. So what happens if I just say mi is 2 times ni, or the biggest, something that sets the whole thing to an integer? Then you lose all your constraints. And in principle, this would be right, and it's dangerous to the argument, but actually other Swampland constraints come to the rescue here. So again, if I can set mi to be arbitrarily large, so this is just a parameter of a supergravity theory, and these are pretty much hard to constrain just from supergravity results, right? But this mi also appears when I want to, when I go to the dual formulation in terms of this modified Bianchi identity for the dual 2-form field in 8 dimensions. So in 8 dimensions, the 4-form is related to a 2-form. And this coupling, the topological coupling before to the 4-form would translate to this modified Bianchi identity for the 2-form. And now this 2-form couples to strings in the theory, just by completeness hypothesis. This must not be tensionless or light. This can be, in principle, very heavy. However, you have to be careful because there is anomaly inflow onto these strings, and this is highly constrained. And so, for example, since these are supersymmetric BPS strings, there is a constraint that is space-time dependent, and for d equals to 8, you will find that your left-handed central charge has to be smaller or equal to 18, right? And in order to cancel the anomaly inflow generated by these modified Bianchi identities, I know that this already contributes like that to my theory. And another Swampland constraint tells us, actually by Miguel and Kumrun, tells us that in 8 dimensions, we know that there can only be a rank 2, rank 10, and rank 18. And if you plug in 18, you can choose whatever gauge algebra you like of rank 18. You will find that this is always equal to 18, only for mi equals to 1. So for the rank 18 case of the gauge group, this, yes.
That's true for AD algebras only.
So yes, that's right. So in the non-simply laced case here, but you can never go below that bound. It will always go up. So it is. So I think that is right. That is only true for ADE, but you will find the same bound that in rank 18, these mi are actually fixed to be order 1. And this bound that I told you before, that this has to be an integer, is very efficient in ruling out global realization of gauge groups in 8 dimensions. Okay, so that's that part. That is great. But we know. Sorry, is there a question?
Yeah. Can I ask quickly? So just follow up on what Marina said. So for non-simply laced in rank 18, we can. So what is the values of MI that we can have? Like 1 and 2 or something like this? Or?
You mean in the lower rank cases here?
No, I mean rank 18. So maybe misunderstood.
No, I think in rank 18 it's really fixed to m equals to 1 for all the
I thought Marina was making a point about rank 18.
No, I was making a point that this inequality is, I mean, the equality of it is not satisfied
I
necessarily.
see.
Okay.
That's right.
Right. So for like symplectic groups, I see in CH.
Okay, so this is the field theory side, and it works great. We found like a constraint on the global realization of the gauge group in supergravity, just taking into account like a new type of mixed anomaly involving the center one form symmetries. That's great. There's no reference to string theory yet. However, we do know how to construct these models, and especially the rank 18 case on which I will focus because the constraints are the strongest here. And this is given by F-theory compactified on elliptically fibered K3 manifold. So just a one slide review of F-theory. So this is the geometrization of the axiodilaton into an auxiliary torus, if you wish. And in fact, all the gauge algebras contained in the AD theories will be given in terms of 7 brane stacks on this base, which is just given by a two-sphere, a P1. And the gauge algebras are specified by the Kudaira classification in terms of the singular fibers here. And the global data that we're interested in, like the global realization, the factors of subgroups of the centers are given in terms of the torsional sections of the Mordell-Weil group, right? And the intersection pattern of the torsional section, so the full geometry and the full data thereof determines this completely for us. So let's check what we can actually find in F-theory. So how is this done? I told you this has to do with the intersection pattern of the torsional section. So let's go to an example, which is an SU6 gauge algebra. So once I resolve this fiber singularity, what actually pops out is this affine Dynkin diagram of SU6, which is given just by these 6 spheres connected. So the zero section will always intersect the affine node. And now the torsional sections can intersect different nodes in this resolution divisor. For example, if it intersects here, I will know that the global realization is given by SU6 mod Z6. It could intersect here, then it's SU6 mod Z3. And it could intersect this node, and then it's SU6 mod Z2. And well, in these geometries, because K3 is very, very well known, you can actually find math papers discussing geometrical constraints on elliptically fibered K3 manifolds, right? And what happened to us when we opened this paper by Miranda and Persson is that we found these constraints for a theory that only has SU type algebra fibers. And if I go back 1 slide or 2 slides, no, 3 slides, then you will find that this guy here is exactly the same thing, right? So with mi equals to 1. Now we're in the rank 18 case. So somehow this mixed anomaly constraint in field theory points towards K3 compactifications of F theory. And this, I think, is in itself a beautiful result and points towards a concept that can be called string universality. So in fact, everything that is consistent, and we found an additional consistency constraint in this mixed anomaly, comes from string theory. And in this guise, it comes from F theory on K3. Of course, the lower rank cases are a bit more complicated and the constraints are not as simple, but at least for the rank 18 case, this is a very strong restrictions on what is allowed. Okay, so now I want to change gears a bit and describe more why string theory is so constrained. So now we have a field theory reason.
Markus, sorry,
yes,
because I think you're changing gears. So can I go back? So
yes,
you have this thing with the MIs, right? Like and you
right.
constrain them with the inflow argument. does this work also in 6 dimensions? Because in 6 dimensions you will have a similar thing happening, right?
So in 6 dimensions, so you're basically saying, can I constrain the self-intersections numbers from anomaly inflow constraints?
Right. So in 6 dimensions you get them. You get exactly what the.
So in 6 dimensions, this is at least from a string construction perspective. These are given by intersection numbers. If you again are obnoxious to string theory and just say, like, let's take whatever integer,
right?
Then I might get constraints on these. And I think there are papers that I probably, yes, I think in these papers, they also have constraints for lower dimensionality.
Right. No, but I mean, but you kind of want the MIs not to be, so you in the 8-dimensional case, you were playing really with the fact that you're close to saturating the bounds, right? So when I'm asking is
that I think the main constraint, so the main thing that doesn't allow us to generalize this to 6 dimensions is more the fact that we have a bunch of tensor fields suddenly, right? That couple differently to all these subsectors. And we already seen that there, in principle, there are non-trivial constraints in 6D. For example, I have to combine a couple of things in order to find anomaly-free combinations. And I think these constraints, in principle, they would hold true also in a gravitational theory. So if you define a gravitational supergravity theory in 6 dimensions, you would also, with, let's say, this SCFT sector coupling to it, I think these constraints hold true. And in principle, there is a landscape to explore, I would say.
Okay, thanks.
Okay, so why is string theory so constraining? Why are these torsional sections so constraining? So what is a torsional section? A section is just a point on the torus fiber in the F-theory compactification that I can add to itself a bunch of times and I end up with a 0 section. So what I showed you here is a picture of the torus, so just with a sides identified and a Z2 torsion point. So if I add this point to itself, which is really in this presentation just the addition law for complex numbers, I will end up here, which is of course identical to this, and the same for these 2 other torsional sections. However, if I demand that the F-theory compactifications leaves these torsional sections or a subset thereof invariant, what I do is I restrict the duality group from SL to Z down to a congruent subgroup gamma. And in F-theory compactification, at least on K3, these congruent subgroups that can arise in this way are highly constrained. So there's only these 7 single factor guys and these 5 2-factor guys. There cannot be any more because you only have a 2-dimensional lattice of torsion points on the torus. So congruent subgroups of SL to Z are just given by these mod n conditions on the form of these SL to Z elements. And this might be a bit confusing why this is the case, but it's actually not that confusing. So if you consider just again the 2 torsion point and think about the T generator of SL to Z, right? So what happens is I go around in my P1 on the F-theory base and I go around something that implements a SL to Z transformation. And what I do is I want to follow this point that is the 2 torsion point here around that guy. So what happens if this SL to Z transformation is given by T? This 1/2 tau will be mapped to 1/2 tau plus 1/2, right? So this is a problem. It doesn't come back to itself, so the torsional section would be destroyed. However, instead, if I take T squared, then the 1/2 tau point will be mapped to 1/2 tau plus 1. And of course, we know that up to torus translations, the lattice of the torus, this is the same as 1/2 tau. So this SL to Z transformation, T would destroy the torsional sections, T squared would preserve the torsional section. And in this way, this is, of course, can be done for all the elements of SL to Z. You will find that demanding the invariance of torsional sections in F-theory compactification reduces the duality group down to a congruent subgroup. But if you do that, suddenly you see that your moduli space gets enhanced because now you have additional data defined on the F-theory fiber. And instead of modding out the upper half plane by SL to Z, I just mod it out by this congruent subgroup. So in the standard string theory textbook, you will find the fundamental domain of SL to Z given by this region here that usually contains a couple of special points, right? So this can be cusps like the one at I infinity, or it can be elliptic points like these 2 points here. Now, in the case of gamma 2 congruent subgroup, which would preserve a Z2 times Z2 torsional sections, I get this enhanced moduli space here. And instead of elliptic points, now I get 3 cusps. And you can think about, if you want to think about this as a real moduli space of your theory, these cusps and elliptic points are holes that are cut out of your moduli space. So these are the elliptic points are related to orbifold singularities actually, and your cusps are related to actual holes. Now,
could I ask you a question about
yes.
that? So if you just go back a slide, yeah. So this modified moduli space, as I understand, is the moduli space of, say, elliptic curves with some extra structures, Z2 torsion point or something.
Yes.
But physically, I'm a little confused about what the meaning is. You know, the duality group in type 2b is SL2Z. Are you talking about a different 10D theory with a different duality group? Or...
Right. So what I'm talking about is restrict your moduli space of your full type 2b or to your F-theory compactification to the slice that preserves the torsional section. Because on this slice, I know that I have this global modification of the gauge group for the gauge algebras involved. And this is exactly the point for that I mentioned before when I said there are complex structure deformations that destroy that. So for example, if you consider 2 7 branes, right, that they would in principle encode something like a T squared, and we've seen T squared preserves this torsional section, right? But I can separate them slightly, and then the whole thing would not preserve the torsional section anymore for paths that only encircle one of them. So this is really, if I restrict my F-theory model to have this torsional section and to be invariant, then this leads to this enhancement of the moduli space. But yes, I agree that physically there are complex structure deformations that destroy these torsional sections.
So perhaps another way of Jake's question is that when you say you restrict it, do you have a physical mechanism or you're mathematically restricting?
No, I'm mathematically restricted.
Well, then why would you do that? In other words, for example, I don't know if you're, for example, trying to get CHL string in F-theory description or what, but
no.
Sorry?
This is just to explore the realizations of these factors of the global gauge group in F-theory compactifications, right? And for that, I know that I have to have distortional sections around. Otherwise, the factorization becomes trivial, and I have no one-form center symmetries to play with, so to say.
So you're exploring a different moduli for the rank 18 theories, what extra symmetries you can get. Is that what you're doing?
Yes, yes.
Okay, that's fine.
Right. So I basically want some other physical reasons of why F-theory only have this very restricted set of torsional sections. I can destroy them by complex structure deformations, but I want to know why only these play a role. So there is a relation between these special points, so the elliptic points as well as the cusps and branes, because simply as I told you before, if I go to 2 points that are related by a SL to C transformation, these usually will encircle one of those special points and implement the SL to C transformation. So for example, for the red path, I would encircle the cusp at I infinity. For the blue path here, I would, for example, encircle the path around I, which is an elliptic point of the modular curve. And by encircling this path, I mean that I will have to implement the SL to C transformation by going around it. And of course, now I map my space-time manifold into the modular curve. This is just a way of giving the values of tau and whatsoever in a space-time dependent fashion. And I have to have something that implements this SL2Z transformation. And of course, we know in F-theory that the something are 7 branes because they have this SL2Z transformations around them. So what happens if I include my 7 branes in your theory, then what you actually get, what you will find is that you compactify your modular curve, so to say. So before you had these holes, now you fill them, which means you have the object that implements the SL2Z transformation, and I know what to do in order to pull the path on space-time through the brane, right? So this will compactify the modular curve, and we know that the compactification in this way will lead to Riemann surfaces. Now, in a Swampland paper by Hirose and Kumrun, what was actually done was, what was conjectured is that the moduli space has to be trivial when it comes to 1 cycles, right? So now we have the compactified modular curve, and we want it to be trivial when it comes to the 1 cycles, but this restricts it to be of genus 0. So after the inclusion of all the branes of the model, what you will find is that in order to be in accordance with this conjecture 4 of the paper, you have to have the Riemann surface to be the 2-sphere. And there is only so many genus 0 congruent subgroup, and if you compare, you get exactly the ones that you got from the K3 compactifications in F-theory, right? With a couple, so this couple meaning this is these two-factor theories here, and no, sorry, this is also a 2-factor theory here, and 3 1-factor theory that are not realized. So this is
confused. I'm a bit confused.
Yes.
The conjecture we had with Hiroshi was about the moduli space of the vacuum with no restriction on the complex structure. You're restricting it in subspace, if I understand you correctly. So we didn't have any specific conjecture about that, unless there's a chance I'm misunderstanding you.
I see. So what you're saying is that the full moduli space has to have a trivial.
Yes, that was what our conjecture. You're kind to refer to the extension of it as our conjecture.
Okay, so maybe
as our conjecture, but maybe you have something else extending.
Yes, so maybe I should say that this is then an extension of, if I restrict the moduli space of these F-theory models, where I demand the invariance of these torsional sections, then then
it should be genus 0. How would you phrase that in a Swampland way without referring to geometry? So can you phrase that in such a way that it could be viewed as an extension of a conjecture we had with Hiroshi?
So I would, and I will come to that in the remainder of the talk, I would more refer it to something that smells a bit more like the cobordism conjecture. Okay. So it's like I have to have objects that trivialize what I have.
Okay, I'll wait for that.
Okay.
Can I ask a quick related question? Sorry.
Yeah.
I'm very confused, again, when you say you're deforming away these rational sections. I mean, when you say tuning, do you mean tuning within the space of a general toric model over that base? Or do you mean that for one smooth geometry with fixed Hodge numbers, you can actually destroy those torsional sections?
Well, in principle, so for example, if you go to the K3 model, right, and just take the type 2B perspective, for example, there is a complex structure deformation that would separate 2D7 branes, right? So
in K3, I could buy that because K3 moduli space is a funky thing, but for threefolds, I would be surprised if that can happen.
Okay, so this argument, we only did it for the K3 case, yes. So maybe there might even be a more general and stronger argument for the lower dimensional case, which would be fantastic because that is pushing it down to lower dimensions. So what we know
is questions. I would be surprised if you can actually, I mean, I think for one geometry, this is everywhere in the moduli space, what you're saying. I don't think you can destroy torsional sections.
Okay, that's great. That's great. So then this would also answer Kumrun's question, I guess, for lower dimensional compactifications. Yeah. Right. So yeah, in lower dimensional, So in fact, also the constraints here, so the congruent subgroups in lower dimensions are not as, so there's some that are not allowed. For example, the K, the gamma 1K with K equals 7 and 8, you will not find in F-theory compactifications on Calabi-Yau threefolds. So maybe this can be even generalized to that, which would be great. So with that, let me come to the last.
Sorry, because I see you're saying. Can you go back for a moment? Like, what's the? So you said that the extra cases can be realized by a few exotics. What do you mean there? Like that's.
So what I mean is that you cannot realize it in terms of a K3 manifold, because if you check the genus 0 subgroups that are not in these K3 classifications, you will find that you would have to add a number of branes that would oversaturate your 24 singularities in the K3. However, if you consider like more crazy models, right, these would break supersymmetry, so all the arguments are a bit harder to justify. But if you put a cosmological constant on the sphere that allows you to put more branes, right? So if you have no constraint anymore that there is in principle only 24 I1 fibers but more, then maybe you can realize these. And this has been discussed in this paper by Kleban and Dierigl.
Could I instead of talking about a compactification, talking about 7 branes in flat space? Because there I would have no.
If you, yes, for example, if you would forget about, if you don't care about any more of 8D gravity theories, but you care about 8D objects in a 10D gravity theory, and ignore the back reaction of the branes induced by a deficit angle, yes, then I think this is also justified to say that those could be realized by these.
And then you get a perfect match between what you can do with 7 branes and these genus 0 subgroups. Is that right?
I think so. To carry this argument further, you should have the gravity in the game. So I'm not entirely sure if you should understand it in terms of. So for example, if I just take a stack of 1,000 D7 branes, right? This would, in principle, locally respect a order 1,000 section, because it's just T to the 1,000.
Okay. I see.
So it's not, maybe it's not so unproblematic to.
Okay. So these exotic cases, we don't know how to.
So these two, we know that they don't arise on K3 compactification.
Right, but
the question is. But
you were explaining like you would want to do it by turning on like a cosmological constant, but that's not something that I know how to do in type 2B string theory. That's right. That's why I said more unusual setups, because we don't know how to implement it in a very reasonable way. Exactly. It's just this constraint doesn't seem to restrict these very few cases that are left over, and this was our way to. Maybe fantasizing how they might be realized in physical.
But the cases that you said Reddy and Kleban are doing were non-supersymmetric and time dependent, right?
Yes, that's right.
So this is not this is a completely different ballgame, I would say.
That's right. So that's why I said that we have not the same measures to control what is happening.
Could there still be some other compactifications we are unaware of with this much supersymmetry? Would these realize as these cases?
Good question. I don't know. It's not K3.
Can it be K3 with frozen singularities?
So K3 with frozen singularities, it's more like CHL related. And I would also assume that a similar constraint holds. But yeah, we haven't explored this. This is another topic that is very interesting to explore.
We have. We can discuss that later.
Okay, so did you find something like a Z10 or Z12 factor in those theories, for instance?
No.
Okay, yeah, this is what I would have.
No, not in 8 dimensions, but if you go to lower dimensions, I'm pretty sure. But no, I don't know. They might arise, yeah.
Okay, cool. Thank you. So what I said before is like this. First of all, the compactification of the moduli space by including branes, and the necessity to include branes for the consistency of the theory sounds a little bit like the cobordism conjecture. which basically tells you that all realizations of quantum gravities, as well as their compactifications, have to be connected. In mathematical way to phrase this is that the quantum gravity Bordism group has to be equal to 0. We don't know what quantum gravity means in that setup. We can just put in as much as we know of the structure that we know that the quantum gravity should have, right? So one way that this can be pictured is you have this space, and in order for this to be 0, all spaces that I allow should be deformable to a point. So this is also this null Borden condition. However, these deformations are not general, but they depend on the structure I impose. So for example, it could be spin structure, it could be pin structure, or gauge fields might enter the game, or higher form fields, which modify the whole thing. Now you put what you know into this Bordism constraint. If you find that it's non-zero, then you know that something has to happen. So either this has to be broken, which means that there are objects that you didn't know about that you should add in order to trivialize the Bordism group. This is exactly sort of what we find here, right? And the other possibility is that your quantum gravity theory only makes sense in a certain subset of theories, which could be described as gauging of what is left of this Bordism group and implemented by constraints on your backgrounds. So now what I told you is, and let me go back to the type 2B setup. So what we know is we have this SL2Z duality group, and I should be more precise. The duality group of type 2B is actually not SL2Z. It's rather something like spin MP2Z, or even more exotic like the pin plus cover of GL2Z. But for this talk, let us just be a bit more well, ignorant about that and focus on this sort of bosonic duality group. And I can assure you that not all of these classes that we have to include would be killed by even doing this more abstract way. So what we have is we have type 2B, and now we want to compactify type 2B on a circle down to 9 dimensions. And what we can do is we can do a non-trivial duality twist around this circle, right? Because we have the duality group, and we demand, because now this is where it's not completely correct, we demand a spin structure on the manifold. Usually the spin structure actually mixes with a duality group into this twisted Bordism classes. And then we can just check what the Bordism group of this guy is. This can be calculated, for example, by Atiyah-Hirzebruch spectral sequence. And you will find that it's given by Z2 plus Z12. And for this untwisted version here, this Z2 is nothing but the spin part, and the Z12 is actually coming from the abelianization of the SL2Z. And you can understand what is happening. So what is happening is you go around the circle, you do a SL2Z transformation. So all the SL2Z bundles are just given by exactly this transition function around the circle. However, these Bordism groups, they are generalized homology theory, so they're abelian. So you don't see the full SL2Z, rather you see only this abelianization thereof, which holds true also for congruent subgroups here. So you would find the Z2 from the spin structure and a factor that corresponds to the abelianization of the congruent subgroup. So we see indeed we have to add something. So we have to add something for the spin structure, but more relevant for us here, we have to add something that trivializes this guy. And this is the 7 branes, right? But now actually we see that even the D7, the perturbative D7 branes would be enough to kill the abelianization of the SL2Z. So you somehow lose this non-abelian structure. And this non-abelian structure I want to stress is very specific to complex codimension 1 objects, right? Only then you can really have this non-abelian statistics between particles, which we can track by doing our business with having this path on the modular curve. That is capable of remembering the full non-abelian statistics of the objects, whereas this more coarse but more general. So this would now be even true for non-supersymmetric configurations. I think the only constraint is that the objects associated to that have to be of finite tension. However, you lose part of the information in these subsectors potentially. So in that sense, it's nice how these different aspects of Swampland and conjectures intertwine to give us non-trivial results on string theory and effective field theories constructed. So in that, I want to conclude my talk in a twofold way. So I think there's two ways to think about the Swampland program. The first one is more like draining the Swampland. So you could study your field theory or your gravity theory and try to find new constraints, as we did, for example, by including the center one form symmetries, that leads to a richer anomaly structures and obstructions to gauging, and gave us constraints really by anomalies in terms of the global realization of the gauge groups, and also Swampland constraints for quantum gravity, just in this 8D supergravity framework. But then we found the beautiful thing of relating that to an interpretation in string theory itself, and in our case, the F-theory geometry on the compactification on K3. And this pushes us towards the string universality. So even in field theory, we only encounter models that can be constructed from string theory and even have like a nice interplay of string geometry and like generalized anomaly constraints, which is a beautiful thing. Another way to go is more related to like charting the landscape, right? You could take another standpoint. You can start from string theory, which is in itself highly restricted. For example, the realization of torsional sections in F-theory model is in itself highly restricted, which of course in consistent compactification descends down to the EFTs, which might be a guiding principle to lead to a deeper understanding of the real world. And well, potentially even give us at some point some quantum gravity constraints that tell us what the gauge group and not only the gauge algebra of the standard model is. So, and with that, I give you a short outlook, which is just this slide that should emphasize the beautiful interplay of what could happen is like the interplay between dualities of string theory, then higher form symmetries and Bordism groups that might lead to a nicer unified picture of what we're doing, even in EFTs, as well as string theory itself, and hopefully leads to new insights. And I'm pretty sure that there will be a lot of interesting results in that regard in the future. And with that, I want to thank you.
Okay, thanks a lot, Markus, for the very nice talk. More questions, comments from our